Today I want to demo a simple Monte Carlo simulation of geometric Brownian motion. Monte Carlo simulation is one of the most useful techniques in quantitative finance. What we are walking through here will be very basic, but I hope if you can follow this simple demo, it'll be a good start, and you could then extend the knowledge to more sophisticated models and use it for more advanced applications. What we are going to do is to simulate the geometric Brownian motion, which satisfies this stochastic differential equation. We're going to use Apple stock as an example and generate Monte Carlo path. Look at the simulated path and the actual history. Also compare the theoretical expected values and medians with what we get from the simulation and see if they match each other. I'm going to use Jupyter Notebook and Python 3. We first need to import the modules we're going to use. We're going to use numpy and pandas for numerical analysis, which are the most common, basic, yet powerful packages. It's always good to add comments to make your code more readable, so let's do that. We will also need this matplotlib package for visualization purposes. It's the simplest but also very powerful visualization package in Python. There's a lot of other great visualization packages in Python, but that's for another day. Here, I'm adding something interesting here, percentage symbol inline. It is a magic function that renders the figure in a notebook, so you can see the figure right in the notebook. It's super useful. We will also need to download the actual stock history. We will use the package yfinance to download the history from Yahoo. A better solution is actually to build a database first and just read the history from the database locally, because you don't really know when Yahoo's going to stop providing these free services. But for demo purposes, we're going to use this yfinance package. One thing to note is that all these beautiful packages are written and maintained by non-profit individuals and groups. That's quite typical in Python and one of the greatest open source achievements. Finally, here we'll leave some room for whatever additional modules we may need or may not need later. Let's first download the history of Apple stock. We'll use the history from 2018 to 2019 as an example. Let's first define a ticker in yfinance, AAPL. Then we'll call history the history method with start date the last day of 2017 and end date the last day of 2019. We're going to set auto adjustments to false so we can download the actual history prior to dividend adjustments. Note the close will still be adjusted for splits, which in fact makes it very convenient for the user. We're going to take a quick look as well. It's always good to print out some key values and visualize the data, at least for sanity checks. Okay, let's press Shift plus Enter to run this block of code. Note in Jupyter Notebook, if you hit Shift and Enter keys together, you run the code in that cell. And you have multiple options for that cell. It can be code, markdown, or notebook convert, and heading. The notes here are actually written as markdown, which can parse LaTeX formula and symbols. So super useful if the notes and comments are teamed with math. Okay, press down Shift, then Enter to run this block of code. Here we go. We're looking at the first and last values. We started from the last day of 2017 and ended at the last day of 2019. We see open, high, low, close, adjusted close, volume, dividends split. They look all consistent. Looks very good. Ideally, we should cross-validate the data with another source other than Yahoo Finance to assure data quality and integrity. But let's skip that step here. Next, let's plot the history. What's good about pandas data frame is that it's integrated with matplotlib quite well. So we can just do plot, close, instead of doing plot x-axis or y-axis. An alternative way is to use pandas plotting method itself, but that's for another day. With high, low, close, we could also plot candlestick with some other packages, such as MPL finance, but let's stick to the basics. We're going to set the labels, date for x-axis, and the stock price for the y-axis. Now press Shift and Enter. There we go. Sorry, there's a typo here. Here we go again. The history of Apple stock price from last day of 2017 to last day of 2019. It looks right. We probably should cross-check on Google Finance or other data providers, but I think we have the right close history. Now that we have the actual history of the stock, we're going to follow the geometric Brownian motion, SDE, and run a Monte Carlo simulation of the stock in the same 2-year period. Looking at the SDE, what we need to generate is that at any given time, the approximation of the infinitesimal steps. Here would be ds to s. And then we need to multiply it by the stock price S and add that back to S at the current step to obtain the price S I plus 1 at the next step. First, we need to define the step size and the number of steps. In principle, they can be arbitrary, but a natural choice is to just use step size of 1 business day. And then the number of steps would be just how many business days we have, the length of the actual close history. Next, we need to determine how many paths we are going to simulate. We'll start with 10,000. The number of paths certainly depends on how long the history you are trying to simulate and the configuration of the machine you are using. Otherwise, the more the better. Now we are going to initialize the data frame, the container we are going to use to store the MC realizations. The index will just be the dates from the actual history. The columns will be the names of the path. We're gonna just name them from 1 to NMC. So we are naming the path with the numbers from 1 to 3 to 10,000. For all the paths, we are going to set the value on the first day to be the actual stock price on the last day of 2017. That's going to be our initial condition. We also need to know what the volatility is. Note here the volatility is annualized. We probably should use the actual realized volatility within this period. But for simplicity, we are going to assume it's 25%, which is in fact not far from the actual. The drift is a little tricky. It's supposed to tell the average growth of stocks like the one we are starting here, but it's linked to economic cycles and other factors, and no one really knows for sure at any given time. In Black-Scholes model, drift should be replaced by the risk-free rate under the risk-neutral probability measure. For our purposes, we're going to assume it's 8%, which is roughly the long-term average annualized return for large caps. However, this is not risk-neutral assumption, so we should be aware of that. Remember, we select step size to be 1 business day, but not everything is in unit of year, so we need to turn this one business day to year. We have 2 years, and excluding the first day, which is initial condition on the last day of 2017, we have dt equals 2 divided by nt minus 1. We can print out the daily volatility. This is probably where you want to pay extra attention. The sigma times dwt we are going to simulate is for the step size of 1 business day, which has standard deviation, that's daily, which is sigma times square root of dt, the step size. So that dwt squared would be just dt, as you may have learned. Okay, now having everything, we are ready to generate random paths that follow the geometric Brownian motion SDE. We're going to use a for loop to do this one step at a time. More advanced developers can think of faster vectorized way to achieve this, of course. At every step, we are generating ds to s following the SDE. Drift times dt plus sigma times square root of dt times a random number following normal distribution. We're using numpy's random number generator package to generate random numbers. And then we will update the next step from current step with ds to s, which is generated. Okay, shift plus enter, we go. Sorry, there's a typo here. Should be range, not range f. Actually, note you can use tab key to autocomplete existing functions and methods. Sometimes you may type too fast, like I just did, but using tab is almost always more efficient. Here we go again. We should have populated ST with a simulated path that follow the desired geometric Brownian motion SDE. We are going to do some sanity checks. We are going to randomly select some MC path and plot them with the actual, just to see if there's anything obviously wrong we have done. I'm using add underscore subplot from matplotlib. It's a very convenient way to make multi-panel plots. Here I'm only plotting one panel, of course. You should do some research on how to use it. It's very useful. Let's use the choice method from numpy's random package to randomly select 20 paths from our simulation. Now we're going to plot each path in blue color and line width 0.5 so the plot is not too busy. Note here, I in STI is just the name of the path. Remember earlier we named the path or the columns just with the numbers, so we can just use them to select the path. And we are going to plot the actual in a red color and with a slightly thicker line. Okay, show the full plot. This may not be necessary actually. Also, let's add a comment to remind ourselves that this is to show the actual for comparison with MC realizations. Anyway, shift plus enter. Here we go. The blue ones are the randomly selected 20 simulated MC realizations. The red one is actual. If we randomly pick one of those blue lines, can we trick people that it's the actual? Looks pretty good. Let's run it again and randomly select another 20 realizations. Okay, try it again. Good. And again. Okay, looks pretty decent. That was just some sanity checks. To see if we are really doing things right, let's compare the expected values from our MC simulation with theoretical values. Remember, by solving the SDE, the theoretical expected values is simply S0 times e to the drift times t, and the median has minus half sigma squared t in the index, so it is smaller than the expected value. Okay, now let's calculate the mean from the simulation first. We're just going to use the mean method. Notice we specify axis to be 1 here, so we are calculating the mean every row over all the columns. Note the result is a pandas series. Next, we calculate the theoretical one. Is 0 times e to the drift times t. We here use numpy's a range to generate all the time steps. The result is a numpy array, so we're going to turn it into a data frame with the same dates as index as actual. Here we can use series too. You don't have to use data frame. Let's add a comment to make sure this is more readable. Let's print out the last value and see if they match. The last value of mean from the MC simulation, the last value from the theory. Shift plus enter. Okay, 49.9 from MC, 49.6 from theory. Looks reasonable. Now let's plot the mean as a function of time for both our Monte Carlo simulation and theoretical expectations. We should just see an exponential function as we saw in theory. We're going to use add underscore subplot as well. Okay, MC mean, th mean, say the x label, date, say the y label, expected value, and also we should add the legend so that we know which is which. Okay, press shift and enter. Here we go. We see the blue line is the expected values from MC simulation, while the orange line is from theory. They're pretty close. Looks like we're doing things right. Next, let's do the same for the median. We're going to do the exact same thing. Medians from Monte Carlo, MC median with axis 1. And the medians from theory, th median is 0 times exponential drift. Here we need to subtract half sigma squared, then times the time. Again, this is a numpy array, so let's turn this into a data frame with the index the same as the actual history states. Finally, we are also going to print out the last values for sanity checks. The last value of MC median, then the last value of the theoretical median. All right, press Shift and Enter. Sorry, there's a typo here. Okay, fix the typo. Shift and Enter again. Good. MC median, we see MC median is 46.4, the last value, but the theoretical median is 46.6, so it's pretty close. Note this is smaller than mean as it's supposed to, because we have to subtract half sigma squared in the formula in median. Next, again, let's plot the median values from the Monte Carlo simulation and compare them with theory. Actually, let's just copy what we did earlier and change all the means to median. Okay, just Control C, Control V, change all the means to median. Great. Press Shift and Enter. Cool. Note the median from Monte Carlo simulation now looks noisier than the mean, which is expected. So far, so good. Next, we're going to modularize what we did. In software engineering, it's always good practice to make your code modular, whether in object-oriented language or functional language. Here, we're going to do something simple. We're going to create a function. In this function, we're going to generate the simulation. We're going to take the actual history as an initial condition. We're going to take in the number of paths, the drift assumption, and the assumed volatility. In fact, let's just copy the whole block of code we did earlier when we were trying to generate the simulation. We can just do Control C, Control P. Note we can do Shift plus Tab to indent the whole block in Jupyter Notebook. Then we copy the for loop. Shift Tab, indent. And then we need to remove the ones we defined as arguments or keywords, since they are going to be passed in. Don't forget to return the simulated path, st, at the end. Okay, Shift Enter. Now we have defined a function that can generate Monte Carlo simulation. Okay, let's generate a new set of paths, say 20,000 of them. And let's do what we did earlier. We're just going to go back, randomly select 20, and plot them with the actual history. Looks pretty good. Now we can also look at the mean, just like earlier. Earlier with 10,000 paths, we have 49.9, versus 49.6 in the last values. Here, the mean is 49.85 from Monte Carlo simulation. So that's a little closer to theory, as expected, since we are generating 20 paths here. Sorry, 20,000 paths. As I said earlier, what we have done above is actually very basic. But hopefully we can apply what we have accomplished here to more advanced models and more sophisticated analysis. One natural application of Monte Carlo simulation is for derivative pricing. We can try to price European calls and puts, the simplest derivatives, and compare the results with Black-Scholes formula. Note you do need to be careful with the drift parameter because Black-Scholes assumes risk-neutral probability. Okay, hope you find this helpful, and I hope to see you next time.